Hello guys, welcome to this lecture. So in the previous lecture, we looked at the various types of organic rearrangement reactions. We discussed that there are two main types of organic rearrangement reactions. We said that there are intermolecular rearrangement reactions and then intramolecular rearrangement reactions. For the intra-rearrangement molecular reactions, we said that there could be rearrangement on electron-rich systems, rearrangement on electron deficient systems, and then rearrangement that involves free radicals, then rearrangement on aromatic nuclei. For the rearrangement on electron deficient systems, we mentioned that there could be different types. There could be the Favosky rearrangement, pinacol, semi-pinacol, allelic rearrangement, Wagner-Meerwein, and then isonitrile-nitrile rearrangements. Now in this video, we are going to discuss the Wagner-Meerwein rearrangement. This rearrangement involves the migration of an alkyl or an aryl group to an electron deficient cationic center. Now let's look at this reaction that is shown below here. Now this reaction, let's label the carbons from left to right. So carbon 1, 2, 3, and 4. Now let's do the same to our product side. We have carbon 1, carbon 2, 3, and then 4. Now from the labeling, we see that this carbon 2 here has 2 methyl groups attached to it. Then when we come to the product side, this carbon 2 here also has 2 products attached to it. Now when we come to this side, carbon 3 here, it has 2 methyl groups attached to it, whereas this carbon 3 here in the product side also has 2 methyl groups attached to it. So clearly this is not an example of a rearranged reaction, because this product here is not a rearranged product. Now let's consider the second reaction here. Now if you do the same labeling from left to right, carbon 1 to 4 in both the reactants and the products, and then let's label this other carbons here. Let's call this carbon 5 and call this carbon 6. Let's call this 5 and then 6. So we have 6 carbons. Now in our reactant side here, this carbon 2 here has 1, 2, 3 methyl groups. When we come here in the product side, this carbon 2 here has only 2 methyl groups. In the same way, if we come to this carbon 3 here in the reactant side, it has 1 methyl group, whereas in the product side, this carbon 3 here has 2 methyl groups. Now if we look closely, realize that carbon 2 here has carbon 5 and then carbon 6 attached to it, whereas carbon 2 here only has 5 attached to it, besides the one that is in both sides. Now carbon 6 that is attached to carbon 2 here is now attached to carbon 3 in the product side. So clearly this is an example of a rearranged product, and this is an example of the Wagner-Meerwein rearrangement. Now let's look at the mechanism that is responsible for this rearrangement reaction. So for the initial steps, we have the oxygen of the alcohol picking up a proton. We form this H2O molecule here, which is a very good leaving groups. It leaves and then we form a carbocation. Now the steps that follow this carbocation generation here can be divided into 2 steps. There are 2 main concepts that's used to explain the Wagner-Meerwein rearrangement. We have the classical ion concept and then the non-classical ion concept. Now for the classical ion concept, now for simplicity's sake, let's make our CH3 group here an R to make things simple. So after the carbocation has been generated in this step here, now it's important to note that these two carbons here have different hybridizations. This one here is now sp3, is still sp3 hybridized, while this one here now is sp2 hybridized. So we can represent this with the shape or the actual shape of the molecule, right? So this methyl group, these two methyl groups here, one is pointing away, the other is pointing towards us, and then the positive charge here is carried in the empty p orbital. Now it's important to note that the R group here is in the same plane as the p orbital. Now what happens is we have the electrons forming this bond here being migrated into the empty p orbital. Now as this happens, we see that the R group migrates from this carbon here to this carbon, as you see in this intermediate. Now after the migration, a base comes in to deprotonate this hydrogen. The electrons forming this bond here are delocalized here, and then we have a rearranged product. So this is a classical ion concept. Now let's look at the non-classical ion concept. Now in this concept, after the carbocation has been generated, it is purported that the bond between this carbon here becomes partial, whilst a partial bond between this R group and this carbon here is being formed. So as shown in this intermediate here, there's a partial bond here and a partial bond there. That means that this bond here is the bond between the sp3 hybridized orbital of this carbon and the sp3 hybridized orbital of this carbon in the R group. In the same way, this bond here is between the sp3 hybridized orbitals of this carbon here and the carbon in the R group. So we have a geometry of the molecule or the intermediate that looks something like this. So this here is sp3 hybridized orbital of this carbon. This one here is sp3 hybridized orbital of this carbon here. And then this here is sp3 hybridized orbital of the carbon in the R group. So we have a net positive charge localized in the partial three-membered ring. So a base comes in, abstracts the proton, electrons in this bond here are localized in here, and we have a rearranged product. Right, let's look at some more examples. Another example we could look at is the hydration or dehalogenation of alkyl halides. So we have an alkyl halide here, and then we add that with silver nitrate. We form a primary carbocation, and then this primary carbocation can rearrange to form a tertiary carbocation here. So what happens is any of these two methyl groups can migrate onto this carbon here, that we form this intermediate. If the oxygen attacks this carbon there, we form this product here, which is the hydration product. If the oxygen abstracts a proton here, the electrons are delocalized here, we form this product there, which is the dehalogenation product. Now another example we can look at is the hydration of cyclocarbonyl chloride. Now this example is very important because this illustrates how Wagner-Meerwein is used to explain ring expansion. So in this reaction, we see that we generate a carbocation in this first step here, and then there's a rearrangement to form a 4-membered ring from a 3-membered ring. Now we also see that this reaction produces two products. Now the yields of these two products are very close. So the question is, why do we have high yields for both the rearranged product and the normal product? The reason is simple. We have a resonance structure that is for the two carbonium ions that exists rapidly. Now let's see what I mean by this. Now after we generate the cyclocarbonyl carbocation, the ring expansion can happen in two ways. we can have a migration of this side of the ring or that side of the ring. Now, if the first side of the ring expands, we have this intermediate here. And then if the second side of the ring expands, we have the second intermediate here. That means that there are two possible bicyclobutonium ions that could be formed. Now, these two resonance forms have a net resonance form that looks like this. Now, this bisected cyclocarbonyl ion here provides an extra stability for the intermediates formed, and hence we expect to have high yields. Now, terpenes are also prone to Wagner-Meerwein rearrangement. Now, according to the Markovnikov rule, if we add an acid or a hydrogen, a proton, to this pinenes here, we expect that the hydrogen goes to the side where there are more hydrogens. So in this first reactant here, we expect the hydrogen to go to this side here. Then in this second reactant here, we expect the hydrogen to go to that center there. So in both cases, we form the same intermediate. Now, at a very low temperature, we form this product here. However, if we increase the temperature, this group here migrates to that carbon there. Then we form an intermediate, a rearranged intermediate. That looks like that. So at high temperatures, we form a product, the Bonal product, instead of the normal product. The reason why this is stable is, if you look at the both conformation for this structure here, it will look something like this. We see that this conformation here is stable. So we form this at high temperatures and this at low temperatures. Now our last example here is for this complex mechanism here. Now if we add this reactant here, impurine with sulfonyl chloride, this OH group becomes a good leaving group. It leaves and reforms this carbocation here. Now this carbocation generated here undergoes a series of ring expansions as shown the red arrows, and we form this intermediate there. Now a base comes in, abstract this proton here, then we form our alkene here. Now it's important to note the stereochemistry of each sentence there. So this R group is pointing up towards us, while this is pointing away from us. This is very important to avoid steric hindrance. Now before we end today's lecture, let's look at another phenomenon we call the anchimeric assistance. This is another type of rearrangement that occurs with the help of a nucleophile that is in the neighboring carbon. An example is when we have a beta-beta-beta triphenyl ethyl chloride, as shown here. What happens is, in formic acid, the electrons in this benzene ring here is donated to this carbon here and pushes this chlorine away, as seen in this intermediate. So we form this phenomion ion here, which is very stable. Now these electrons here can be localized into the benzene ring to form this intermediate here. So we hydrate our carbocation here to get our sulfolysis product. Okay guys, this brings us to the end of today's lecture. Thank you. I'll see you in the next lecture.